In this video, we'll go over IR spectroscopy and really just focus in on the key information that is obtained from the IR. Just briefly, we'll go over the electromagnetic spectrum as an overview to see where the IR fits in into that spectrum. We'll go over the Hooke's model just to explain that and look at the spring constant effect, and we'll look at a reduced mass effect. I'll do a problem just as a proof of principle, and then just some general remarks on the key info obtained, and then I'll go through a few examples just to show you some different regions of the IR that may be lighting up or showing a signal versus others that are not, and try to propose structures and propose really functional groups that could be present, but maybe more importantly, functional groups that aren't present in a particular structure based on the information that you're seeing in the IR. So that'll be helpful, I think. IR is best used in parallel to other spectroscopy methods. For example, IR is really useful when you have an NMR also available. Okay, you can't really determine a structure alone just by IR, but it does offer key information to the functionality that could be present in the structure. But usually other spectroscopy methods are present or available as well. All right, so the regions of the electromagnetic spectrum that are relevant to the IR is the IR region here highlighted in pink. And what the type of energy that this allows is for molecular vibrations. Okay, so the IR region is just enough energy to allow bonds to start to vibrate, which means they're stretching and compressing, and so you can see signals based on that. And the difference in bonds between functional groups gives different signals along the axis of the IR spectrum, okay, within sort of this range here. And so as you increase the frequency, you're increasing the energy. As you increase the frequency, the wavelength gets longer. So frequency is inversely proportional to the wavelength, knowing that E equals the Planck's constant H times the frequency V. All right, so the Hooke's model is really more or less just the ball and spring model. So if you have two atoms connected by a spring in between them, in this case, let's say a bond, then as those atoms stretch and compress, they're going to do so at different frequencies depending on what the mass of those atoms are that are attached to the bond. Okay, so energy equals some, again, Planck's constant times the resonant frequency, and that can be in frequency is equal to the speed of light divided by the wavelength. So there's a relationship between frequency being inversely proportional to wavelength, and that can all be equal to this term right here, which inside this term, we can look at factors that are affecting where along the axis the signal shows up. So we have K, that's the spring constant or the force constant. And these values can be looked up, but we can assume that all C bonds have the same force constant, or all CH bonds, let's say, have the same force constant. Okay, what's different though is that a double bond has a different force constant than, say, a triple bond. So the rigidity of the bond is different, and that's reflected in where along the axis you'd start to see the signals. The other term here, mu is our reduced mass term, and this is really dominated by the light atoms. So I'm going to do a proof of principle problem just to show you what I mean. Okay, this value here, V bar, that is wave number. And so wave number is proportional to the frequency, but inversely proportional to the wavelength. Okay, so 1 over wavelength equals wave number. Okay, and that's why the units are inverse centimeters, because wavelength is a unit of length, typically we're using centimeters. So that's inverse centimeters, where V bar equals 1 over wavelength. And so there's a relationship between V bar and frequency now. As you increase the frequency, V bar gets higher. All right, so let's think about a problem here. And so comparing a CH versus a CD stretch. So, hydrogen and deuterium are very similar in their functionality. They're both essentially hydrogen atoms, but a deuterium atom has one mass unit higher. Okay, so there's a difference in mass now. So when we look at mu, we'll be able to see a ratio of the reduced mass for the CH stretch versus the reduced mass for the CD stretch. So a problem to demonstrate this, let's suppose we have a typical sp3 carbon CH stretch, and that is around 3,000 inverse centimeters, just below, but let's round to 3,000 inverse centimeters. Estimate the vibrational frequency for a sp3 hybridized carbon that's bonded to a deuterium. Okay, so the molecular weight of carbon is 12 grams per mole, and the molecular weight of hydrogen is 1 gram per mole, and the molecular weight of deuterium is 2 grams per mole. And we can assume that the force or the spring constant for the CH stretch is about the same as the CD stretch. So we'll just kind of assume that's kind of a constant number. And from this equation here, also, we can assume that this is a constant as well. And so that's why I'm saying that is just a constant, because that's 1 over some constant, the speed of light. So 1 over 2 pi times a constant is a constant. Okay, so the strategy to solve this problem and think about this is we want to find a ratio of the wave number for the CH stretch to the CD stretch, because once we know that ratio, then we can approximate just by knowing the CH stretch where it kind of shows up, we can approximate where the deuterium CD stretch would show up in the IR. And then I'll show you an IR to say, hey, that approximation's pretty close. But what we'll also notice is that by just changing the mass of the hydrogen from 1 to 2 using the deuterium, there's a huge effect here. And that's because the light atom really dominates what's going on. So just changing the light atom here between a carbon and a hydrogen, we're going to change the hydrogen and make it just 1 mass unit higher, and we'll keep the carbon mass sort of constant. That's why we're using carbon in each case. Okay, so to solve the following ratio, we want to know that ratio will give us a sort of a conversion factor. All right, we'll estimate the vibrational frequency for the unknown bond. Remember, lighter atoms will cause an increased frequency in the spring, okay, or in the spring that's vibrating. I should put a quote around that because it's a bond. Increase the frequency, increase the wave number. You also increase the energy to vibrate that bond. Why? Because it's a stronger bond. And so it has a stronger bond association energy. It takes more energy to pull that bond to a point where it starts to think about breaking. All right, so applying the Hooke's model, okay, we've got the equation shown, and I'm going to set up a ratio. I'm going to apply this equation to both cases here, okay? And so you can see I've set up the reaction 2 different times, or the problem 2 different times, because I wanted to look for a ratio. I'm trying to get a conversion factor. So if I know the CH stretch wave number, then I can use the conversion factor to figure out the CD stretch. And so a lot of this is going to simplify, because you can see here and here, those are just constants. And so I'm just going to cancel them out, because they would just cancel each other out in the equation. And that simplifies the entire equation down to really looking at the reduced mass term. Okay. And so let's solve for the reduced mass. Reduced mass is M1, M2 over M1 plus M2. And then we're going to do that for each bond type. So I've done that for both the CH bond, and I did that and I get about 12/13, and that's approximately 1. So I'm just going to round that to roughly 1. If I do the same thing for the CD stretch, I can see that I plug in the numbers for the masses, M1, M2, M1, M2. So it's M1 times M2 over M1 plus M2 by just changing the mass from 1 of the light atom to now 2. That changes the number to almost approximately 2. So the reduced mass term is about 2 there. And so now I've got myself roughly a ratio here. Let's look at that. And so we're going to plug that into our previous slide, where now we know what mu is for each case. It's 1 for the CH and 2 for the CD. And so I just plug those numbers in here into my simplified equation, solving for that ratio. And I got the square root of 2 over the square root of 1, and that simplifies even further to the square root of 2 over 1. And so when you do the math, the ratio of a CH over a CD stretch is 1.4 to 1. So it takes 1.4 times the frequency to vibrate a CH stretch versus a CD stretch. Okay. And so now we can estimate where the CD stretch would show up. And so I just plug that into the ratio here. I use that ratio to solve for now the VD stretch. And I know that a CH stretch is roughly around 3,000 inverse centimeters. I rounded it up a little bit, but it makes the math simple. So I would expect to see, if I had one, a CD stretch at around 2150. But more importantly here, the difference in these numbers are pretty significant. Okay. And that's just by changing the mass of the lightest atom by 1. Okay. And so there's a big effect. The light atom dominates the term. Here's the IRs that we can look at. I've chosen to use chloroform because there's just a CH stretch that we'd show in the non-fingerprint region. The CL stretches show up down here. And so I've kind of let them out of the picture. And so we're really just focused in here. And then a roughly 21 to 2200. And that's about where we show up. We see a different stretch for the CD stretch. So these are 2 different IR spectrums, 1 for each compound. But you can see by just changing the hydrogen to a deuterium, the peak shifts. Okay, it's now in a completely different zone. And that's what we expected just by solving that simple calculation. You normally won't have to do all of that, but I thought it was a good proof of principle to show you the reduced mass effect and how that light atom dominates. So let me just say some general remarks about the IR. The IR is good for determining functional groups, but not structure. You need other information to do that. The radiation energy must equal the energy to vibrate a particular functional group bond. Look at the peaks in each of the 5 zones, which I'll go over. I think that's a lot easier than trying to memorize tables that give you range of values. Those tables are useful, but I typically don't even use those tables unless I'm trying to really dial in on the exact wave number, okay, if I were given an IR. Here, all vibrational modes, I'll just simply refer to as stretches, okay? I won't get into the weeds with bends and wags and different types of modes. We will not analyze the fingerprint region in this video. In order to have a signal, you need to have a change in dipole moment as the bond is stretched or compressed. So if you have symmetry in the molecule about the bond that you're trying to consider, you're not going to see a signal in the IR for it. So you got to have some small change in dipole moment. Now this, except for bonds to hydrogen, all other single bonds, so sigma bonds, appear in the fingerprint region, and that includes your CX, so your C halogen bonds, carbon-carbon signal bonds, carbon-oxygen single bonds. Those all show up in the fingerprint region, and so we're not going to be looking at those. Nitro groups, the NO stretch, there's 2 different NO bonds, and so you see here for a nitro group, you get stretching that's symmetrical versus asymmetrical stretching. So a nitro group often shows up as two peaks, and it also does so right near the fingerprint region, but it's just to the right of what I'll call zone 5. So it's kind of tricky to see that one sometimes, but it gives really strong signals also. Alkynes that have symmetry around the triple bond will not show a very strong signal if the two R groups are pretty close to the same thing. So let's say an ethyl and a methyl, right? There's not a huge change in dipole there, but it might show a small signal, but it's just not that unsymmetrical. Terminal alkynes will show up in the IR really nicely because they'll give two peaks. You'll have one in zone 1 at around 3,300. That's your CH stretch for the sp hybridized carbon. And then you'll also have the triple bond stretch at around zone 3. And that comes right around 22, 2150 or so in that range. But it's pretty easy to spot because it's in the middle of the IR. And then you'll also have that CH stretch present. Amines or amides, I'll just talk about amines, a primary amines. So these have an NH2 group. So primary has an NH2 group, while secondary only has one NH attached, so one NH bond. So primary amines are going to show two stretches in zone 1. And secondary amines or even secondary amides, they're going to show only one NH stretch. Okay. And that's because, like the nitro group, if you have a primary amide, you're going to get the symmetrical stretching or the asymmetrical stretching. So that's why it's showing two stretches. With just a one NH bond, you're not going to see any more than one stretch. Tertiary amines don't have any hydrogens on the nitrogen. And unless they are protonated under, say, low pH conditions, you wouldn't normally see a tertiary amine. You might be tricked into thinking it's an alkane or some sort of an alkyl group. At low pH, if you could measure the IR, then maybe you'd see an NH stretch at that point. So alcohols and carboxylic acids, these generally have a broad peak in zone 1, and the broadness comes from the hydrogen bonding properties of alcohols and also carboxylic acids. Okay, so this is just sort of a generic IR spectrum, just kind of showing you some of the anatomy of the IR. We have on the x-axis, you have your wave numbers. And so if you go left to right, you're changing the numbers. And so a higher wave number is on the left, lower wave number on the right. And the wave number is really just an expression of the frequency, as we talked about earlier. And so there's more frequency needed to vibrate a CH bond than would be, say, a CX bond, okay? On the left is percent transmittance, okay? So that's gonna be dependent on then what kind of signal you're seeing. Is it a strong transmittance or not? Where it's flat, there's no IR energy absorbed. And I will also mention that CO2 is very abundant in the atmosphere. So you're always going to see CO2 in the IRs. It's hard to get rid of. Okay, so let's start looking at the 5 zones. And so I've broken up the IR into 5 main regions: zone 1, 2, 3, 4, and 5. And the zones are based upon what kind of bonds are showing up. So zone 1 is mostly bonds to non-carbon atoms, except for the alkyne CH, which shows up at around 3,300. And so my cutoffs here are right about here. That's about 3,300. Okay, and so zone 1 starts around there and goes all the way up to 4,000 or roughly. So you're going to see most of your OHs, your NHs in zone 1. Zone 2 is all your CH stretches. There are 3 different types to look for. Your alkene CH, so your sp2 hybridized carbons, those are going to be around 3,200 to roughly 3,150 or so, give or take. But they're going to be above 3,000 usually. Your sp3 CH stretches, these are all going to be less than 3,000 in this region. And then your aldehyde CH stretch, this is around, I'll say 27 to 2850 or so. Sometimes you'll see that show up. Aldehyde CH stretches are really characteristic in the IR. So if you have an aldehyde, you're going to see it. Zone 3, it's really just reserved for the triple bonds, except here, and look, you can see CO2 was present in there as well. CO2 has an sp hybridized carbon, and that's why it's in zone 3. So zone 3 is really just triple bonds. So that means these atoms are all sp hybridized. Okay. Zone 4 is all your carbonyl bonds, and there's lots of different types. Those from an aldehyde, ketone, ester, carboxylic acid, and even the amide. Those all show up in zone 4, and that's roughly 17 to 1800 or so. The amide is a little bit lower than 1700 because it's got a lot of alkene type character in the CN bond. But then zone 5 is your carbon-carbon double bond. So if you have an alkene or an aromatic ring that has a carbon-carbon double bond, you're going to see that roughly around 1600 or so in the IR. Anything beyond 1500, I'm not going to look at in this video. I'm just going to call the fingerprint region. So if you expand the non-fingerprint region a little bit, you can kind of see more closely where those ranges typically are. I've also included a table here. It's generic that kind of gives you some different ranges for each of these different types. So over here, I've got the functional group type, the generic structure, the frequency range, and then where I kind of would expect to see it in terms of what zone. So I don't really like to use these tables unless I absolutely need to. These numbers over here, I just have rewritten over here just to kind of give you some clarity. I thought it was easier to represent them on the right side of this table just for space. And then on the left here, that's telling you what kind of bond stretch, okay? And then what type of CH bond. So if you have a CH bond, you need to specify what type of carbon it is. Is it sp, sp2, sp3, or is it the aldehyde carbon? Otherwise, you don't know, okay? So it's not clear then. So let's start looking at a few examples. I have example 1 here. I've got 3 main non-fingerprint region peaks highlighted, and I've also shown you what zone they're in, okay? So functional groups that we can rule out an alcohol or a carboxylic acid because we don't see a broad zone 1 stretch. Okay, that's a sharp peak. We don't have a primary amine because we don't have the doublet for the primary amine. Okay, we can rule out alkenes or benzene derivatives because there's no zone 2 CH stretch that is greater than 3000. That should be greater than. So let me fix that. Okay, so we would expect alkenes to show up on the other side of 3000. Whereas sp3CH stretches show up on the right side of that number. Okay, so I don't see that stretch shown is greater than 3000 at all. There's no carbonyl stretch, and that's because you don't have anything in the range of zone 4. It's completely empty. Okay, so there's no carbonyl at all. Possible functional groups, we could have a secondary amine. We could have a terminal alkyne because I see a zone 1 stretch. I could have alkyl groups. Obviously, most compounds have alkyl groups in them. So you're going to see the CH for an sp3 carbon a lot of times. That usually shows up in many of the IRs. We could also have a nitrile, okay, or an unsymmetrical alkyne because in zone 3, we see the stretch. So something that stands out to me is that I've got a peak here and a peak here. So I start to think that maybe I have a terminal alkyne here. right? But without more information, it's hard to really nail that down. Okay. So that's why the IR is useful. It allows you to kind of rule out functional groups that your structure doesn't contain. And it also gives you some clues what it might be in terms of functionality. I think I might have a terminal alkyne. And in fact, the IR here is for heptine, and that is a terminal alkyne. Okay. But you can see that characteristic CH stretch in zone 1 coupled with the C triple bond C stretch in zone 3. All right. So what other pieces of information might be helpful here? Molecular formula, because we can look at degrees of unsaturation. That would be helpful, or an NMR. And so we can get a lot more information from an NMR structure because it tells us about connectivity, what's nearby. We can determine number of protons from an NMR. We can look at how the atoms and the bonds are connected really closely. Okay, example 2 here. Now I've got a zone 1 that's empty, so I'm not going to have any alcohol or amines or carboxylic acids, or I'm not even going to have a terminal alkyne. I do have a bunch of stuff here at the zone 2 for the sp3ch stretch. You can see once again that this peak here, it's less than 3,000. So I don't have an sp2ch stretch that I see. I have something of weak signal that I've highlighted in zone 1. One reason why that might be weak is it's almost symmetrical. Is what we can think about. And so I've shown the structure for this IR. I've got a triple bond in 2-hexyne, but if you think about the dipole, the change in dipole that would result from stretching this triple bond, it's not going to be a huge change in dipole because on both sides of this, I've got pretty similar functional groups. They're both alkyl groups. And so I'm not really influencing the dipole that much by either one of those in terms of differentiating the dipole. Okay, so, but once again, I have an internal alkyne, so the zone 1 CH stretch is no longer there. Okay, once again, what other pieces of information would be helpful to rule out a nitrile? So that's a this. I could have had, why didn't I have this? For example, so other pieces of information that would have been helpful, a molecular formula, a mass spec, an NMR even would have been helpful, I think, to kind of rule that out. So again, the IR is good at giving you a little bit of information, but it's not great at giving you the entire structure. Here, I've given it to you. Or if you think you know what the structure is, that might be helpful. Example 3 here is for benzyl alcohol. I just wanted to show you an example of an alcohol. So if you look at zone 1 now, I've got this broad OH stretch, and it almost covers up peaks in region 2 or zone 2, the broadness of that. So sometimes if you have water in your sample, it's going to cover up the entire region in zone 1 and 2. So we don't take IR, so water, not a good IR solvent, mainly because it's not volatile. So it doesn't evaporate easily, and the OH stretch is so broad, it masks peaks of interest. Right? So for example, if I tried to apply this benzyl alcohol to the IR in the presence of water, maybe we're trying to use that as a solvent to get it to stick to the plate, then we would then see the water show up. A lot of IR machines today, they allow you just to put the compound right on the IR machine itself without the need for any solvent. So that's nice. You can also put solids right on the IR machines now. And so also nice. You can kind of just leave solvents out of the picture. But if you do have to use a solvent, it's best to use a solvent that has a really low boiling point, so it evaporates very quickly. So solvents of choice, diethyl ether is a good one. Dichloromethane. Also known as methylene chloride. These have low boiling points. And so they're not going to show up in the IR and interfere with the signals that we are interested in. Okay. So some other peaks here that we notice here, mainly the zone 1. So that leads me to think I've got some sort of an alcohol or maybe a carboxylic acid. Zone 2, we have a couple different things going on. You can see that my 3000 is sort of my benchmark here. I've got peaks on both sides of 3000. And so I've got possibly an sp2 carbon that's bonded to a hydrogen, but also sp3. So I have some sort of an alkene and alkane. That makes sense because I've got the CH stretch for an sp2 carbon. And then I've also got others for the sp3. So you see those both in the IR. Sometimes these show up, sometimes I do not. At around 17, 18, 1900, these are overtones for the aromatic compound. And so we won't go into why they're showing up or why they're not. Just know that they don't always show up. And if they don't show up, it doesn't mean you don't have some sort of an aromatic system. Benzene is an aromatic ring. This is showing up very nicely in this IR, so that's kind of a bonus. Zone 5, here we are right around 1600. You can see that if I draw a line straight down the x-axis, right where I would expect to see a carbon-carbon double bond stretch. And so that's where my aromatic carbon-carbon double bond stretches are showing up. And so all the pieces here for benzoyl alcohol, but again, without me giving you the structure of benzoyl alcohol, you may not have guessed that was the structure responsible for this IR. Example 4, I wanted to show you because here's a nice one where you see the aldehyde CH stretch, and it's different than a normal sp3 CH stretch. It's different from an sp2 CH stretch. It's on the low end of zone 2. And if you look down here at my axis, it ranges between 27, 2800 roughly. And so if you have a CH stretch, that's the aldehyde CH stretch, that's this CH stretch right here, you're going to see it in the IR, but then you should also check zone 4 and see if you have a nice carbonyl stretch, which I do. So I think that those two peaks right here and right here, they talk to each other. Okay. Without one, you wouldn't have the other, right? Without the aldehyde, you're not going to have that CH stretch. Okay. So if you have a ketone, you wouldn't see the CH stretch, but you might see a carbonyl stretch. Why is this not a carboxylic acid or an amide? Because you don't have zone 1 lighting up. Why is this not an alcohol? Same reason. Okay. So I think this could be a ketone or ester because of the carbonyl, but then the aldehyde's really confirmed right here by that CH stretch. So I'm going to rule out that that was an ester or even a ketone at that point. Okay. And so this is the structure for isobutyraldehyde. Okay, so here's a structure or an IR where I'm not giving you a structure, right? So you have no idea what the compound could look like. I've also given you a molecular formula just to show you how that might be helpful, because you can calculate the degrees of unsaturation for that formula. So I like to call this SODAR, degrees of unsaturation means the sum of double bonds and rings the sum of double bonds and rings, SODAR. Okay, so that's 2 times the number of carbons plus 2. Okay, so that's 2 times 8 plus 2, that's 18. Okay, plus the number of nitrogens, that's 19, minus the number of hydrogens. 19 minus 11 is going to give us 8. 8 divided by 2 is 4. And so 4 is telling you you have 4 rings or 4 pi bonds or a combination of rings and pi bonds that would equal 4. So just a lot of different variation in the structures, right? But what you see here is some pieces of information in the IR. It looks like there are both sp2 and sp3ch stretches. Possible. I also have something in zone 3, so that tells me maybe I have a carbon-carbon triple bond or a carbon-nitrogen triple bond in zone 4. That leads me to believe I have some sort of a carbonyl, but I don't think I have an aldehyde because I'm not seeing anything light up where an aldehyde peak would show up. It's kind of empty. So I'm ruling out, the aldehyde. And then in zone 5, right at about 1600, those are pretty typical for your C double bond stretch. Okay. But more information would be helpful, like proton NMR, carbon 13 NMR, mass spec, to help me deduce or figure out what the actual structure is. Okay. So we've talked about some possible functional groups, IR, NMR, mass spec. These are other methods that can also be coupled and looked alongside the IR to really nail down a structure. Okay. So once again, I just kind of note that. And so I'll leave it at that. I don't know the structure for this IR, but it kind of raises the issues that one could have. I've hypothesized what I might think it could be. But again, we just don't know yet. So I'll leave it at that. I hope this video was helpful and that you enjoyed watching this, and thank you for your time.